The data streaming in from the transiting exoplanet survey satellite has just shifted our entire perspective on what is happening right now in the outer reaches of our system. We are not looking at a static model anymore. We are looking at a 28-hour continuous video sequence that fundamentally rewrites the visual history of interstellar Comet 3I Atlas. This isn't a simulation. This is raw footage compiled by Daniel Muthukrishna from the Massachusetts Institute of Technology, spanning from January 15th to January 22nd, 2026. What we are seeing is the comet as a distinct, bright luminosity dragging a faint, stubborn tail across a densely packed starfield. It is racing away from us, appearing as a magnitude 11.5 object. To give you a sense of what that means, it is roughly 100 times fainter than what your naked eye could pick up in a perfect dark sky. Yet, it is blazing clearly through our orbital telescopes. But there is a glitch in the narrative, quite literally. If you examine the timestamp continuity in this new release, you will notice a jarring jump. The footage goes dark because the transiting exoplanet survey satellite effectively shut its eyes, entering an emergency safe mode triggered by unexpected issues with its solar panels. We lost telemetry right when the observation was getting critical. However, what we did capture before and after that gap is providing the first real-time confirmation of the comet's 7.1-hour rotation period. We are seeing repeating brightness patterns, a rhythmic wobbling in the tail structure that suggests the nucleus is tumbling in a very specific, periodic way. Before we go deeper into the physics of that rotation, I want to pause on something that makes this data set even more unsettling. While we are all watching it leave, the team at MIT found something staring back at us from the past. It turns out the satellite had accidentally photographed 3I Atlas back in May 2025. That is 2 full months before astronomers even knew it existed. Think about the implications of that. The machine saw it before we did. By stacking over 9,000 individual images from that pre-discovery epoch, researchers have managed to retroactively trace the visitor's inbound trajectory through our cosmic backyard. We usually rely on back calculations to guess where an object came from, but now we have hard photographic evidence of its approach vector hiding in plain sight in the archival server. This retroactive detection acts as a crucial baseline. When we compare that ghost image from May 2025 with the high-contrast footage from January 2026, we are not just seeing motion, we are seeing evolution. We are watching how the solar wind and radiation pressure have physically altered the coma over an 8-month arc. The object leaving our system is not the same structurally as the object that entered it. If you appreciate getting these deep dive breakdowns on interstellar data, the moment the papers hit the servers, make sure you are subscribed to the channel. We are tracking this object all the way to the heliopause, and you will not want to miss the updates from the Jupiter encounter coming up in March. Now, look closely at the tail activity in the new January footage. The dust production has not shut down. We usually expect comets, even the dynamic ones, to quiet down significantly as they retreat this far from the Sun. But 3I Atlas is maintaining a complex morphology. The tail is not just trailing, it is interacting with the solar wind in a way that implies the grains are larger and heavier than typical cometary fluff. This aligns with the rotation data. A 7.1-hour spin is fast, close to the breakup limit for a loose rubble pile. If this thing were a distinct, fragile aggregate, that centrifugal force should be flinging material out in a chaotic spray. Instead, the tail wobble is periodic and controlled. This suggests we are dealing with a body that has significant internal cohesion. It is holding itself together against the spin, which hints that the nucleus is solid, dense, and massive. And that brings us to the real problem with the visual data. The brightness we are seeing from the transiting exoplanet survey satellite is magnitude 11.5. That is unexpectedly bright for an object at this distance, unless the surface area is enormous or the reflectivity is incredibly high. For weeks, we have been debating whether this is a small, shiny shard of ice or a dark, hulking mountain of rock. The video evidence suggests the latter. A small object would not hold this magnitude while shedding this much dust unless it was vaporizing itself into oblivion, which the stable rotation refutes. We are looking at something big. This TESS release is the smoking gun that validates the trajectory models, but it also forces us to confront the scale of this visitor. We are not watching a pebble drift by. We are watching a worldlet. And to understand exactly how massive this worldlet is, we have to switch our view from the wide-field survey of TESS to the precision optics of the Hubble Space Telescope, because the numbers Hubble just sent back are absolutely staggering. The wide-field view gave us the motion, but the Hubble Space Telescope has just given us the mass, and the numbers are frankly hard to reconcile with our previous encounters. Hubble has managed to do something incredibly difficult. By carefully subtracting the surrounding fuzz of the coma, that halo of gas and dust that usually obscures the center, it has resolved the actual nucleus of 3I Atlas. We now have a physical measurement of the solid body itself, and it is a giant. The data reveals an effective diameter of 2.6 kilometers. There is an uncertainty window of 0.4 kilometers, assuming a standard albedo, or surface reflectivity, of 0.04. Let me put that number in perspective, because 2.6 kilometers might not sound like a planet killer, but in the context of interstellar objects, it is a leviathan. This is approximately 40 times more massive than 2I Borisov, the interstellar comet we tracked back in 2019, which had a diameter of only 0.7 kilometers. But the comparison gets even more extreme when you look at 1I Oumuamua. 3I Atlas is at least 20,000 times more massive than that first enigmatic cigar-shaped visitor. Oumuamua was estimated at less than 0.2 kilometers in length. We are dealing with an object on a completely different scale of planetary engineering. This massive nucleus measurement is not just a random figure derived from pixel brightness. It aligns perfectly with independent calculations based on the comet's non-gravitational acceleration. When we track how the object drifted off its pure gravity-driven course, we attributed that drift to the rocket effect, jets of gas pushing the comet in the opposite direction. For the rocket effect to push a rock this heavy as much as observed, the mass loss rates from outgassing had to be immense, and they were. The Hubble confirmation of a 2.6 kilometer diameter provides the missing variable that balances the equation. The physics works. The mass, the outgassing force, and the trajectory drift are now locked in a consistent mathematical model. But this size has terrifying implications for the transparency of our solar system. Researchers now estimate that at any given instant there is at least one interstellar object the size of 3I Atlas within 4.5 astronomical units of the Sun. That is inside the orbit of Jupiter, and this is likely a conservative lower bound. The logic is chillingly simple. If 3I Atlas were inactive, if it were just a dark, dead rock without the bright coma and tail, it would be dramatically harder to detect. We likely would have missed it entirely. This implies that multiple similar visitors, objects kilometers wide, have probably slipped through our solar system unnoticed, even during this modern era of wide-field charge-coupled device surveys. We are only seeing the ones that light up. The Hubble data also highlights a striking activity asymmetry that is puzzling the dynamics team. 3I Atlas is fading much more rapidly now that it has passed perihelion, its closest approach to the Sun, on October 29, 2025, compared to how it brightened on its way in. It is almost as if the object is shutting down. The post-perihelion surface brightness profile is significantly shallower than what was observed before. The slope of the light curve has broken. Usually, a comet warms up, retains heat, and stays active for a while as it retreats, a phenomenon known as thermal lag. But here we see a rapid drop-off. This suggests that the active regions on the surface might be shutting off abruptly, or perhaps the volatile ices that were driving the activity have been exhausted in those specific areas. The nucleus light curve shows clear evidence of temporal variations attributable to rotation modulation, meaning as it spins, different faces are exposed to the Sun and Earth. We are seeing the heartbeat of the comet slow down visually, even as its rotation remains constant. This rapid fading is a critical clue. It tells us something about the surface composition and how deep the heat from the Sun penetrated during that October flyby. If the heat had soaked deep into the core, the outgassing would be sustained and sluggish to stop. The fact that it is dropping off so fast implies the activity is superficial, driven by a thin skin of volatiles that is reacting instantly to the changing solar distance. However, just as the team was getting comfortable with this fading giant theory, the geometry of the solar system threw a wrench in the observations. On January 22, 2026, the Sun, the Earth, and 3I Atlas aligned in a near-perfect straight line. This celestial arrangement created a rare lighting condition that triggered a phenomenon known as the opposition surge. And the magnitude of this surge has opened up a whole new set of questions about the texture of the comet's surface. The opposition surge is one of those optical phenomena that feels counterintuitive until you see the geometry. On January 22, 2026, the Earth sat directly between the Sun and 3I Atlas. From our vantage point, the shadows on the comet's surface effectively vanished. Every dust grain, every crevice, every boulder was fully illuminated, hiding its own shadow behind it. When this happens, the brightness of an object spikes non-linearly. It doesn't just get a little brighter, it flares. And flare it did. The scattered light from the dust grains around the nucleus displayed a statistically significant opposition surge of about 20%. This surge was characterized by an E-folding width of 3 degrees. This wasn't a random fluctuation. It was a precise optical signature that matches exactly what recent theoretical models predicted for a body covered in porous, fluffy regolith. It confirms that the dust grains surrounding the nucleus are not smooth, glassy spheres. They are complex fractal aggregates with intricate scattering properties. This 20% surge is a vital piece of the puzzle because it helps us understand the texture of the light we are seeing. It tells us that the rapid fading I mentioned earlier isn't just about the gas turning off. It involves the physical state of the dust itself. The dust is interacting with sunlight in a way that suggests it is incredibly fine-grained but structured. Let's pause here for a second. We are talking about angles of light and scattering physics, and it can get dense. If you have a theory on why a surface would behave this way, flaring by 20% just because the shadows disappear, drop it in the comments below. I am curious to see how many of you think this points to a specific type of surface erosion versus a primordial coating. What makes this surge even more interesting is how it contrasts with the overall fading trend. Remember, the comet is fading fast as it moves away, yet specifically at this zero-phase angle, it popped in brightness. This isolates the optical properties of the dust from the thermal properties of the gas. The gas production is plummeting, but the dust that is already there is behaving like a classic planetary regolith. This behavior connects back to the nucleus size. A body 2.6 kilometers wide has enough gravity to retain some of its larger particles, potentially building up a surface layer or a mantle of dust that falls back down after failing to reach escape velocity. This fallback process could explain the complex texture required to produce such a specific opposition surge. We might be looking at a world that is actively burying itself in its own fallout. But while the visible light is telling us about dust and rock, the infrared light is telling us a completely different story about chemistry. And this is where the narrative takes a sharp turn into the unexplained. The James Webb Space Telescope has been tracking 3I Atlas alongside Hubble, but looking in the mid-infrared spectrum. Webb sees heat, and it sees molecules. The data it captured in mid-December and late December 2025 has revealed a chemical signature that simply should not be there. We call it the methane paradox. On December 15th and 16th, and again on December 27th, Webb's MIRI spectrometer stared at the comet. At this point, the object was between 2.2 and 2.5 astronomical units from the Sun. Spectroscopically, the team found the usual suspects: water vapor in the 5.8 to 7.0 micrometer range and carbon dioxide around 15 micrometers. They even detected nickel. These are standard cometary ingredients. We see them, we tick the box. But then, at 7.6 micrometers, a massive signal appeared: methane. This is not a trace amount. The production rates for methane reached 13.7% relative to water in the first epoch and a staggering 27% in the second epoch. That means for every 4 molecules of water, this thing was spitting out. It was spitting out 1 molecule of methane. That is an enormous fraction. Here is why that is a problem. Methane is hypervolatile. It sublimates, turns from solid ice to gas, at incredibly low temperatures, much lower than carbon dioxide or water. If methane were on the surface, it should have boiled off way back in August 2025, when the comet first started warming up. In fact, it should have been the first thing to go. But when Webb looked in August, it saw carbon dioxide, it saw carbon monoxide, it saw zero methane, not a whisper. So, how does a comet spend months baking in the approach to the Sun, venting its carbon dioxide and carbon monoxide, and only after it passes the Sun and starts cooling down does it suddenly start venting massive amounts of methane? It violates the standard thermal processing sequence. You don't cook the sensitive ingredients last. You cook them first. This paradox suggests the methane was trapped. It must have been buried deep inside the nucleus, shielded by a crust that was devoid of methane. This implies a layered structure, a differentiation, where the outer shell and the inner core have radically different chemical histories. It strongly suggests that methane was depleted in the outermost layers of 3I Atlas and only got exposed to warming sunlight when the heat finally propagated through that outer crust. Or perhaps when the surface physically fractured near perihelion, exposing a pristine, volatile-rich vein to the vacuum of space. But even that explanation hits a wall. Carbon monoxide is even more volatile than methane. If the surface was warm enough to boil off the carbon monoxide back in August, it should have absolutely stripped any near-surface methane too. The fact that CO appeared first and methane appeared later flips the volatility table on its head. We are missing a mechanism here. Something is preserving the methane until the very last moment. The methane paradox essentially forces us to rewrite the thermal history of this object. If the methane was not releasing until December 25, it means the interior of 3I Atlas was chemically segregated from its exterior in a way we rarely see in local solar system comets. Let's look at the numbers again. In August 2025, the James Webb Space Telescope found the comet was unusually rich in carbon dioxide relative to water. Back then, carbon dioxide was carrying 87% of the total mass loss rate in the gas phase. Water was a measly 4%. Most of the remaining 9% was carbon monoxide. It was a dry, carbon-heavy exhaust. Fast forward to the post-perihelion data from December. The carbon dioxide to water ratio has collapsed. It is either half that amount or similar, depending on which epoch of the MIRI spectroscopy you trust. But the methane has skyrocketed to 27% of the water production rate. This inversion, where the dominant carrier of carbon shifts or the volatile release sequence is scrambled, points to a stripping event. Hypothesis 1. The comet had a processed crust, maybe cooked by cosmic rays, during its billion-year interstellar transit, which depleted the surface methane. The approach to our Sun burned off this crust, and only after perihelion on October 29th did the heat finally tap into the fresh reservoir of primordial ices underneath. Hypothesis 2. The structure is not an onion layer model, but a conglomerate. Imagine two different bodies that smashed together eons ago, one methane-rich, one methane-poor. As the comet rotates, or as thermal fractures open up, we are suddenly accessing a pocket of material that represents a completely different origin story. The spectrometer also detected a significant reduction in overall outgassing over just 12 days between the two December observations. Water activity levels dropped more steeply than other species. Yet, the comet continued displaying an extended source of water production. This means the water isn't just coming from the nucleus anymore. It is coming from icy grains effectively floating in the coma, sublimating as they drift. The comet is surrounded by a halo of self-destructing ice crystals. This brings us back to the sheer weirdness of the delayed methane. If methane implies a pristine, unaltered ice, then 3I Atlas has a core that has been protected from thermal alteration since the birth of its home star system. It has traveled light years, shielded by its own bulk, only to crack open here and now. The chemistry suggests we are effectively sampling the raw nebula material of an alien solar system, material that hasn't been modified by heat for billions of years until this very month. This chemical fingerprint is the closest we have gotten to touching the raw ingredients of another world. And while the Webb telescope dissects the gas and Hubble weighs the rock, we have one final player entering the game. A player that is not looking from Earth orbit, but waiting in ambush near the King of Planets. The next major event will unfold on March 16, 2026. 3I Atlas is not just drifting into the void, it is passing near Jupiter's Hill radius. This is the region where Jupiter's gravity dominates over the Sun's gravitational influence. It is a gravitational chaotic zone, and parked nearby is the Juno spacecraft. Juno is currently operating in an extended mission around Jupiter, but its trajectory and instrument suite allow for a unique serendipitous observation. The spacecraft will observe the comet from a distance of 53.6 million kilometers. That might sound far, but Juno is equipped with a suite of sensors that are designed to measure the intense radiation and magnetic environment of Jupiter, making them incredibly sensitive to the kind of plasma and particle interactions a large comet might generate. We are talking about a full arsenal: optical and infrared cameras, particle detectors, magnetic field sensors, plasma wave sensors, a microwave radiometer, and a radio dipole antenna. This is the kind of close encounter that reveals things optical telescopes cannot. Specifically, the magnetic field and plasma wave sensors could detect if 2.6 kilometers of conductive material interacting with the solar wind creates a bow shock or a magnetic disturbance. If 3I Atlas has even a weak magnetic field, unlikely for a comet, but who knows for an interstellar visitor, Juno will hear it. And while it is the absolute fringe of scientific speculation, this array of sensors, radio, microwave, plasma, is technically capable of detecting technological signals or heat signatures that don't match natural thermal emission. If this visitor is anything other than a natural object, if there is any active transmission or anomalous power source, the radio dipole antenna and the microwave radiometer are exactly the tools you would want listening in the quiet of the outer solar system. We are not expecting a signal. The data points to a natural, albeit massive and chemically weird object. But in science, you don't find what you don't look for. Juno represents our last best chance to scan this object with in situ instruments before it fades into the dark for eternity. The upcoming Juno observation on March 16, 2026, marks the final significant chapter in our active study of 3I Atlas. After this encounter, the comet will drift beyond the effective range of our detailed spectral imagers, becoming just another faint data point in the catalog of objects that passed through and left. But we are left with a composite picture that is deeply unsettling. We have an object with unprecedented mass, 20,000 times heavier than the first visitor we saw. We have a puzzling chemical composition with a delayed methane onset that defies standard thermal models. We have an activity asymmetry where the object shuts down rapidly after perihelion, and an opposition surge that reveals a complex, dusty surface structure. When you combine the sheer statistical likelihood that we have missed many similar objects with the fact that this one was hiding in archival data 2 months before discovery, it forces a conclusion. Our solar system is not a closed bubble. It is a busy intersection. 3I Atlas acts as a wake-up call. It proves that kilometer-scale interstellar bodies are traversing the inner system frequently. The only reason we call this one anomalous is because we managed to catch it. The question that keeps astronomers up at night isn't just, what is this object? It is, how many others are right now passing through the blind spots of our surveillance network? The estimate of one such object within 4.5 astronomical units at any given time changes the risk assessment for planetary defense and the opportunities for future interception missions. We don't need to chase them to the stars. We just need to wait for the next bus. As we wait for the data dump from Juno, the legacy of 3I Atlas is already secured. It has rewritten the book on what an interstellar comet can look like. It is not just a shard, it is a world, chemically rich, physically massive, and behaviorally complex. And as it slips back into the interstellar medium, it takes its secrets with it, leaving us with terabytes of data that we will be analyzing for decades. If you want to support this kind of rigorous data-first scientific reporting, please hit the like button. It tells the algorithm that you value deep analysis over surface-level headlines. And stay tuned. The moment Juno sends back its telemetry from that Jupiter encounter, I will be right here to break it down. Until then, keep looking up.